Let's get restarted. Although I was involved in planning the course, I was not involved in the detailed development of the agenda. But I have to admit, I find it amusing that the radioactive waste management guy immediately follows 5 nuclear chemists. I don't know if there was a message there or not for my nuclear chemist colleagues. All right, let's see if I can work this thing.
Remember, I said we're not throwing over the fence anymore.
That's right. This is the outline of what I'm going to talk about. We're going to, I would say, very briefly talk about the categorization of waste. It's a very lengthy and complex subject. We will try to hit the high points of it. And then we'll try to walk through the major categories of radioactive waste in descending order of hazards. We'll start out with used nuclear fuel or spent nuclear fuel and high-level waste and work on down to low-level waste. And then we'll spend a bit of time talking about the overall regulatory structure for not only waste but for reactors, because we talked about reactors today. And I'll give you some good summary references on the regulatory structure also. So let's get started. Categorization. As you can see, it's very simple. This wiring diagram is intuitively obvious, I think, even to the least informed among us. Of course, it's not. It's a very complex system. It has evolved over a very long time period, and I'm not going to spend too much time on this wiring diagram because I actually don't think it helps very much, but what I will do is point out a couple of categories of waste that we're not going to talk about at all this afternoon. Management of radioactive waste is an entire semester course at Vanderbilt, and we're trying to blow through it in about an hour and a half, so there's some stuff, obviously, that's going to get left out. We will not talk about norm, which is normally naturally occurring radioactive materials. We will not talk too much about mill tailings, although it's a very large waste form. Something had to go, and that was one of the items that had to go. So we won't be able to spend time on either of those. We'll try to touch on each of the rest of these categories above the line. The line here is the division of the types of waste that are codified in the Code of Federal Regulations, the Atomic Energy Act, as opposed to those types of waste that are either defined by DOE order in the case of transuranic waste, or by classification from the Nuclear Regulatory Commission staff in the case of Class A, Class B, and greater than Class C wastes. So with that very brief overview, we'll start with high-level waste. High-level waste is defined as highly radioactive material from fuel processing, including liquid waste produced directly in reprocessing and any solid material derived from such waste. So as you can see, it's not defined by the amount of radioactivity that is in it per se. It is defined by where it came from, which is reprocessing of high level of nuclear spent nuclear material. And it's also the NRC has the ability to add other waste to this category. I am not aware of them having done that. This category is pretty much this definition plus used nuclear fuel, which has to go to a permanent geological repository. Transuranic waste is waste that contains more than a certain amount of alpha-emitting transuranic isotopes and of transuranic isotopes that have half-lives greater than 20 years. Again, except for not high-level radioactive waste. which is previously defined, and it does give the Secretary of Energy, with the concurrence of the Administrator of EPA, the authority to designate other materials as transuranic waste. Low-level waste is radioactive waste that's, it's pretty much defined by exception. It's not high-level waste, it's not spent nuclear fuel, it's not transuranic waste, or it's not byproduct material, which we'll define in a moment. But it's, and NRC, consistent with its statutory authority, has classified as low-level radioactive waste. So they can additionally classify other materials as low-level radioactive waste. Byproduct material is any radioactive material that is yielded or made radioactive by exposure to radiation, incident to the process of producing or utilizing special nuclear material. It is also tailings or waste produced by the extraction, i.e. the enrichment of uranium materials or the extraction of uranium ore. And in August of 2005, there were some additional categories of naturally occurring radioactive materials that were added to this category. So it's, interestingly enough, we now have not only waste defined by where they came from, but now if you had the misfortune to be naturally occurring radioactive material that was put onto the books after 2005, you're in your own special category. We won't discuss byproduct material any further today, again, because of time constraints. Before we leave categorization, though, just a couple of very top-level thoughts. I kind of jokingly say here, high-level waste and low-level waste may seem simple, but it's not. It is highly definitional in character. The definitions, as we've noted, have a number of bases. None of them are necessarily the risk associated with the material. And there are case-by-case exceptions that can be found either by, depending upon the category of the waste, can be defined by either the Nuclear Regulatory Commission or, in the case of transuranic waste, the Secretary of Energy with the concurrence of EPA. So it's not surprising that some people find that a bit daunting and a bit complex when compared to the standards that the International Atomic Energy Agency has issued, which basically lay out two parameters to judge the hazard presented by radioactive waste. First is the level of radioactivity, and they break it into high level, intermediate level, and low level categories, although they don't necessarily specifically define that what those radioactive activity levels should be from a numeric standpoint. They defer that to the specific regulatory agencies of the individual countries. And they also encourage the individual countries to take into consideration further breaking down their radioactive waste by either short-lived or long-lived radioactivity, and they recommend about a 30-year half-life to make that break point. So those of us who are engineers and not, are there any lawyers in the room? Okay, so I can say this without my tongue in my cheek. Those of us who are engineers or scientists as opposed to lawyers sometimes perceive the IAEA's system as a little bit more logical and a little bit more easy to understand. We'll go on and discuss used and spent nuclear fuel, and in the interest of time, I know I can skip the first three slides because I saw them in Alan's presentation, and we'll move right on to interim storage concepts for used nuclear fuel. As I think Alan mentioned, reactors regularly discharge about 2,000 metric metric tons of heavy metal per year in the United States of used or spent nuclear fuel. The fuel generates considerable decay heat right after it comes out of the core, and also in certain configurations can have the potential for inadvertent criticality if it loses its geometric configuration. So once it comes out of the core, interim storage is the next generation. It needs to be kept in a configuration that is critically safe long enough to reduce its decay heat, and then await permanent disposition.
Steve,
Yeah.
we have a stakeholder that is questioning the use of used nuclear fuel definition because it's not defined in the regulations.
Hold on. I think I know. I need to go back one, Joe. Sorry. You have a stakeholder that is questioning the use of the term used nuclear fuel. Yes.
Because it's not defined in the regulations. Is that, are other people seeing that same type of complaint come up, or?
Well, it is certainly correct to say that spent nuclear fuel is the term that exists in the Atomic Energy Act and in the regulations that have been put out by both the Nuclear Regulatory Commission and by the Department of Energy. So that's a correct statement. As Bob Jubin said earlier today, used nuclear fuel is possibly a more accurate term to describe the material which still has available energy value in it. So both terms are in usage in the industry right now, and so I think either of them can be used to properly describe the material.
I thought there were no lawyers in the room, Steve.
No, but there clearly is a tap dancer, right? Okay, I guess I did finish this. Go ahead. So we'll move on to the next one. I did it again. I'm going to put that down. So there are two major concepts for interim storage of either spent or used nuclear fuel. The first step is always going into water storage for that time period where the fuel has so much decay heat that it requires that type of active and high heat capacity cooling. The other rule that folks have to adhere to in their spent nuclear fuel storage pools is they always have to maintain enough space that if they had to discharge the entire present core, they would be able to do that into their spent nuclear fuel pool without having to re-rack or restack. It has to be immediately available space.
That was the original design for many plants. I mean, that's all they could do, type of thing, because they were planning to ship off right away, and they had to put in absorbers and increase the pool size and everything else.
Yeah, there's been because of the lack of a geological repository, and there's been a number of campaigns that have gone on to increase the ability to keep spent nuclear fuel or used nuclear fuel on site. Some of them include being able to stack fuel closer after it cools off, putting in burnable poisons so that you can maintain criticality control with the material closer together, and obviously the next option, which is dry storage, after enough decay heat has been after the fuel has decayed far enough so that airflow can maintain the fuel at the proper temperature can be brought into dry cask storage, and that is normally cooled by natural convection, so it's a much less maintenance intensive way to store the fuel for longer time periods.
Steve, how long does it take before you can put it in dry storage?
Well, about all I can say now is how long is fuel normally kept in fuel pools, and it varies from site to site depending upon how large their fuel pools are. It is in the neighborhood of 18 months to 3 years before they tend to take it out. The exact number of how long it needs to remain in the pool is based on how high a burn up the fuel was taken to. As you saw, the curves that Alan presented when he discussed the radiotoxicity of spent nuclear fuel, it depends on how long the fuel was in the reactor.
Steve, I think,
Yes, Jeff.
They started off more like 10-year-old fuel and they've gone down and down. Holtec right now has an application in for 3-year-old fuel. They didn't want to have a 3-year-old, they didn't need to have a 3-year-old in the past, but they had lots of old fuel that was cheap. Now they're getting more and more hot fuel.
Okay, thanks, Jeff. The issue of dry storage has brought into play the concept of exactly what do we want to do with a storage cask for used or spent nuclear fuel. Do we want to just design it so it can be the short-term repository for fuel while it's on site? Or do we want to possibly design it for both storage and transportation? And when we had a design for a geological repository, they were kicking around multi-purpose canisters that could potentially be used for dry storage on-site, transportation, and then emplacement in the geological repository. You note that I say that that's unlikely. It's unlikely right now because we don't have the design that would meet the final stage. So about the most we could do and can do at the present time is the dual storage, the storage and transportation cask. But most of the casks that are being built right now are simply for storage on site. I have a couple of quick pictures to give you a feel for what some of these things looks like. This shows a fuel element, I think from a pressurized water reactor being placed into a spent fuel storage cask. This is a bit fuzzy because it is performed underwater for shielding purposes. This shows a transfer cask being loaded, a transfer cask being put into a storage cask. And I think, from the railings, you can see this is a very large structure. This shows briefly how a vertical storage cask is moved on site. You can see the shielding provided by the cask is fairly substantial. We have people walking within mere feet of this storage cask. And finally, there are two designs for storage casks for interim storage. The previous one you saw was the vertical one because it was standing up and it's intended to stand up. There's also a horizontal storage casks which go into holding sites that you can see with the circular covers, and this horizontal storage cask is being aligned to be emplaced. This is the present interim state for spent or used nuclear fuel. There are security requirements put in place so that it does not present an attractive target to people who might want to steal the spent nuclear fuel. That includes double fences and razor wire, requirements for monitoring the fuel, and other requirements for safeguarding the material. They are monitored for temperatures in and out to make sure that nothing has occluded the air gaps that are in the casks to ensure flow. I mean, as I note there, these are warm places, and critters do get in them and expire by natural causes. So the issues with this interim state are obvious ongoing maintenance and security costs for the nuclear utilities involved. There are presently about a half a dozen what are called orphan sites where the reactors have been decommissioned, and the only reason that those sites still maintain an NRC license is because of the spent nuclear fuel that's on the site. That's an issue with the stakeholders in those areas. They're no longer getting much economic value out of the site, and they still have that hazard present in their community. In fact, it's one of the major issues that the Blue Ribbon Commission has taken up in their draft reports. And with no geological repository on the immediate horizon, one of the questions that the Department of Energy is having to start to work on is exactly how long is dry storage going to be an adequate and safe form to keep this material in. And that is the subject of research and development under one of the three fuel cycles that the Office of Nuclear Energy is using to organize its R&D efforts. High-level waste. We already defined it. Some introductory thoughts about high-level waste. There are over 220 large high-level waste storage tanks in the Department of Energy's complex. Their capacity is limited, and many of them are exceeding their planned design life right now. You can see that the material is not exactly pumpable. That's a very hard crust on top of one of the tanks at Hanford, so that retrieving the waste can be very difficult. It can be, and it is costly. It's limited not only by the nature of the waste, which we'll discuss a little bit more, but some of the tanks, because of the heating issue that was mentioned, it's been mentioned by a couple of our lecturers, had cooling coils placed in them so that they are not this nice wide open space, but in fact they are a 1,000,000-gallon tank with a forest of cooling coils in it to keep the waste that was put in there to keep the waste cool. There's two ways that we used to cool the waste, either cooling coils, which were used at Savannah River on a number of tanks, or at Hanford the strategy was just to continue adding water in and allow it to evaporate to cool it off. Some of the tanks also have complex geometries because before we learned how much water to add to keep them cool at Hanford, we did have the bottom on some of the tanks buckle and cause some leakage. Some of the waste requires pre-treatment to be efficiently processed by our larger processing plants that are either in place or being built for the long-term treatment. So those pre-treatments require the type of understanding that we've been developing over the last day of the chemistry of the waste, the same chemistry that we understand for separation purposes is the chemistry that we need to understand the pre-treatment of this waste that can be required prior to long-term disposition. For the waste disposition, as I've already said, the waste is non-homogeneous and it can require different processing methods, and we'll discuss some of those for the Savannah River case, where we are already actively processing high-level waste through to its final waste form, if not its final waste disposition. And tank closure. Once we get all the waste that we can out of the tanks, the intent is to fill them with grout to stabilize the structure and close them. We've been able to do that for 2 tanks at Savannah River, 2 that have been finally closed, but there is still an active and ongoing dialogue with regulators and the stakeholder communities on how much waste needs to be removed from the tanks before any more tanks can be taken to that final disposition configuration. So with those introductory thoughts,
I just
yes.
wanted to know, I think that photo on the right is actually maybe Idaho's fluidized bed steam thing.
No, it looks an awful lot like Savannah River to me in the background.
Looks like a picture of Savannah River.
Yeah, right. Yeah, I mean, so it is a picture of Savannah River, but you are correct.
I'm not sure what that is.
But what we were showing is anytime we do work on tanks, it gets pretty complex on top of the tanks. That's kind of the mess that we get into when we want to make entries to our tanks. Yeah, I think it is a picture of tank 48, but it's not yet the steam reformer, right? Good catch. I'll correct the slide for the next use. So from the very high level, what are the major things that we're worried about in high-level waste management? Well, it breaks down into the major categories of adequately storing the waste, developing treatment methodologies for the waste to take it to more stable forms, and then disposal of the waste. So the way underneath storage, the waste is highly radioactive. It generates considerable heat, so your storage methods have to understand both of those factors, and that's why it's typically stored in large, sometimes cooled, well, always cooled in one way or another, underground tanks. Treatment over the long term, the waste form that's approved for high-level waste is glass. Some of the materials that are byproducts of getting the material into a form that it can be made into glass it can sometimes be categorized as other than high-level waste, and therefore they can be handled by, for example, by grouting or immobilization. And we'll talk a little bit more about disposal as we move on. We're talking about the EM complex as opposed to commercial waste and high-level waste because, quite basically, that's where all the high-level waste is. As you've heard from previous lectures, only a very small amount of commercial nuclear fuel in the United States was reprocessed at West Valley. Because the expertise in dealing with high-level waste resided with the Department of Energy based on an agreement made, I believe, back in the middle 1980s, the West Valley site, the remediation of the West Valley site where that reprocessing took place was turned over to the Department of Energy for execution. So I'm going to go through each of the 4 sites in the Department of Energy that has high-level waste, talk a little bit about the origin of that waste, the processing plan for that waste, what its final disposition is, and then for each of the sites, some of the issues that the department is presently working on. Some of the basics, we've already said where high-level waste comes from. The ultimate disposal of the waste is in a geological repository. What this does, this graphic shows you, is we're talking about 100 million gallons of high-level waste, complex-wide, approximately. And I think if you add it up, about 900 million curies, and those, the only thing I would say is all don't have the same date of decay. So it's less than 900 million curies, but it's probably still an awful lot. So that is the challenge that the department is facing, and mostly at Savannah River and Hanford. You'll see that we're a long ways towards remediating the high-level waste hazards at both West Valley and Idaho. We've covered the first bullet. Most of the tanks are more than 30 years old. In fact, most of the tanks are bordering on 50 years old. The lion's share of them are made of carbon steel. The only exception to that was at Idaho, where the tanks were made of stainless steel. Some, especially at Savannah River, are at or near the groundwater table. And some of them have no secondary confinement, as they would have if they were designed initially to be, for example, in Hanford, they're regulated under RCRA, which would require double containment for hazardous waste. We're not presently planning to reprocess any of the used nuclear fuel in the DOE complex, with the possible exception of aluminum-clad fuel at Savannah River. What that means is we probably won't be adding too much to this, to the inventory of high-level waste. So our present need with respect to high-level waste is to store it safely, to get it ready for treatment, to treat it, and then place it in the waste form that is approved as the final waste form for the high-level waste. The numbers there show you the number of large high-level waste tanks that exist at each of the 4 sites, and Idaho has 44 bins in 6 bin sets, and that's a slightly different storage configuration for high-level waste, which I will go over when we get to the Idaho section. High-level waste is stored in a number of different forms. In the large liquid waste storage tanks, we have 3 physical configurations that the material's in. Going from the bottom of the tank up, we have sludge on the bottom, which is the solid material in the tank, and it shows there that it's oxides and hydroxides of various of the cladding materials that the nuclear fuel had, and fission products. There is salt cake, which are sodium salts, hydroxides, and nitrates and nitrites, as shown there. And then at the top of the tanks is supernate liquid, which is mostly at this point sodium hydroxide liquor with most of the cesium that is stored residing in that layer. At Idaho, there was a campaign to process that high-level waste to what was planned to be its final waste form, calcined waste powder. So we have that material stored as calcine in the bin sets that I'll show you, and then as was mentioned earlier in the day, there was a campaign to pull cesium and strontium out of the high-level waste tanks in Hanford, and capsules were constructed from that material for a food irradiation program. Capsules were built largely in the mid-'70s to late '70s. The program was terminated in the mid-'80s because of a couple of problems with the capsules when they were deployed for use. Just a sidebar is that they are still irradiating food in Europe. It's a very common method for preserving food. So those are the forms that high-level waste is in the complex. Other than the enormous amount of radioactivity, which I already discussed, there are other hazards associated with the high-level waste. Even though the high-level waste was created by taking the plutonium and uranium out of the material, there is still special nuclear material, plutonium and uranium in the material. So we have to make sure that actions we take to either change the physical or chemical form of the waste don't cause reactions that would allow that remaining special nuclear material to concentrate and potentially produce a criticality event. And also there's very obvious chemical hazards from all the chemistry that you spent the first 6 hours of today learning that produced this waste material. So on to our geographical tour of high-level waste sites of the Department of Energy. We'll start in northern New York at the West Valley site, which, as I said, was set up as a demonstration project for reprocessing of commercial nuclear fuel. The material was produced between 1966 and 1972. It was stored in 4 tanks on site. Well, see, first mistake. Two of the smaller tanks at West Valley were stainless steel. 2 large carbon steel tanks. There's about 23 million curies associated with the high-level waste at West Valley. The waste processing mission at Waste Valley, I would say, is complete. The material, cesium-137, went through some initial processing, and we produced 275 canisters of borosilicate glass at West Valley. It's stored at West Valley, waiting its final disposition. And you could see a fuzzy picture of that because that, like many pictures it is taken through a viewing window in a shielded cell. Idaho, the next site we'll go to is Idaho. The original site mission at Idaho was as a reactor test station. The number I have is that 52 different reactors were tested and operated at the site over different time periods, and all but one at the advanced test reactor are now decommissioned. The high-level waste was generated and stored as a liquid. Unlike Hanford and Savannah River, it was maintained acidic. As you saw from the Purex process, the Purex process is an acidic process. Since the tanks at Savannah River and at Hanford were made from carbon steel to make them less expensive, because we made a whole lot of them, the material was neutralized with sodium hydroxide and actually kept in high pHs to avoid corrosion of those carbon steel tanks. At Idaho, that wasn't necessary because the tanks were stainless steel. Most of that waste was calcined during runs in the 80s and 90s to produce the calcine that is presently stored in the bin sets. There is some sodium, what is called sodium-bearing waste at Idaho, still awaiting processing. That waste was waste from cleaning out the nuclear waste processing plants at Idaho.
The West Valley, whatever happened to all that equipment and everything? Are they still monitoring it?
So which equipment are you?
The reprocessing equipment and everything in the West Valley.
I will ask one of my Idaho colleagues.
Well, at West Valley, they're going through a D&D of all the
Right,
facilities that
right.
are no longer used. And I think there's a request for proposal out to relocate the 275 high-level waste canisters into a different type of system so they can D&D the current storage location for the 275 high-level waste canisters.
So that means it's still being monitored.
Yes.
Yes. Okay. Just some quick facts about the calcined waste at Idaho. They processed 8 to 9 million gallons of liquid waste during that campaign. As already noted, it produced about 4,400 cubic meters of dry calcine stored underground in 6 concrete shielded structures and 44 individual bins, and these are large cylinders. I mean, they look like cylinders. They're tens of feet tall, 20 to 30 feet tall, approximately. As I said, there's been analysis done of this waste when Yucca Mountain was the anticipated disposition site and the rules were in place. Those analyses in the environmental impact statement for the Idaho site indicated that the calcined material should meet the requirements for direct disposal at the geological disposal site, but because there was never a final determination of that, we're also looking in parallel at what processing would be required to take that material to another more stable configuration. The technology work done by the Office of Environmental Management has decided upon a hot isostatic pressing process for the calcined material. That would be the initial use of this process for high-level waste. For the sodium-bearing waste that I indicated earlier was the result of decommissioning and D&D work because of the lower hazard and the lower radioactivity content of that material. It's being processed by fluidized bed steam reforming, and I believe that it's intended that that's going to go to WIP.
Well, there has to be a formal
Right.
determination made through the processing, so it's kind of debatable. In the state's mind, we should manage that waste stream as if it's high-level waste until that determination's made, so school's still out on exactly what that is.
Okay, so I mean, the department's present plan is that the material is appropriate to go to the waste isolation pilot plant. The final determinations have not been made.
Right.
The ink is not dry on that decision by the department, which would have to have EPA concurrence. The backup technology for the calcined material, if hot isostatic pressing, which, as I said, has not been used for high-level waste form yet, and it also has the challenge that it is not a best demonstrated available technology for high-level waste. EPA presently only recognizes borosilicate glass as an allowable permanent waste form for high-level waste. So if the hot isostatic pressing system either runs into technical problems or regulatory concerns, then the backup technology is vitrification, by either normal joule-heated melters or cold crucible induction melters. This is the sodium-bearing waste that I mentioned earlier. A smaller volume. The Idaho Waste Treatment Unit has been designed and is going through final construction right now, anticipated to be operational by about the end of the year to process this material, and then it's about a 1-year mission to process all the sodium-bearing waste through the fluidized bed steam reformer that's been built to handle that waste form. So remaining issues at Idaho are the sodium-bearing waste, as we've already mentioned. The plan is that it should be able to go to the waste isolation pilot plant, but that final determination has not yet been made. On the and we've already discussed on the side of calcined waste, the hot isostatic pressing system is still in the design and prove-out phase. Vitrification is the backup technology, and their next major challenge is to put in a revised RCRA permit by the end of next year, which has to describe how they plan on moving forward with the waste form in fairly substantial detail. And there are agreements with the state of Idaho that indicates that all of the calcined waste must be treated and ready to ship by December 31st of 2035. That might seem to be a long time away, but the calcine disposition project is going into the same building that it presently holds the integrated waste treatment unit. We plan on reusing that building. So I've actually reviewed the project management estimates for that. 2035 is pretty tight right now. I mean, there is some margin in it, but it's definitely not a slam dunk. Question? This is just a quick cartoon showing you the configuration of hot isostatic pressing, and a even more cartoon version of the cold crucible induction melting system. We'll go across the country to the Savannah River site. The high-level waste originated from a variety of missions at the Savannah River site, mostly for recovery of plutonium for defense purposes, but there were specialty campaigns to make Neptunium-237, specialty campaigns to make plutonium-238, and all three of these processes in the canyons at Savannah River. We went one too far again, I think. All right, no, I jumped to the next slide. All right, so here's the site history. I jumped. Site construction began in February of 1951. A couple of the fuel area was completed by 52. The first reactor went critical in 1953, and two canyons, F Canyon and H Canyon, went online to do the chemical separations required to recover plutonium and tritium later in the middle of the 1950s, and tank farms were built in F area and H area to accommodate the high-level waste produced by H Canyon and F Canyon. I just described this. That's what the tanks looked like at Savannah River as they were being built. Again, you can judge this. Golly, I'm having more trouble than anybody else, and I saw them all have problems. You can get a feel for the scale by looking at that backhoe loader. The tanks are enormous, and getting the waste out of them is a challenge. This is what the tank farms look with the like after the overburden has been put back. And you can say even when we're not trying to do any special operations, there is a lot of equipment on top of these tanks. The equipment is there for ventilation systems, for monitoring purposes, and some temporary enclosures set up for operations purposes and monitoring purposes. This shows you how the waste is distributed along a number of factors in a high-level waste tank. As I said, sludge at the bottom, salt cake on top of the sludge, and interstitial liquids in the salt cake, and then finally a supernate at the top. And the figures on either side show you how the volumes break out in between the various physical forms, and show you that the major amount of the radioactivity is in either the supernate or the sludge, much less in the salt cake material. That will be important to the processing approach and the flow sheet for Savannah River that we'll describe next. This is a high-level process flow sheet. So you can see, unlike the flow sheets you saw earlier, which had individual components, this just shows buildings and what happens in the buildings. The material goes through goes through several processes. The intended long-term products are either borosilicate glass logs produced at the Defense Waste Processing Facility for the high activity fraction of the waste, or for the low activity fraction of the waste to be processed at the saltstone facility into vaults or grouted, to speak in shorthand. The long-term intent is for the salt waste processing facility to be the major processor of salt solution in the tanks, to split between the high activity portion, the cesium, strontium, and actinides that will go to the Defense Waste Processing Facility to be made into glass, and the low activity portion, which can go to saltstone. Highest amount of volume this direction, largest amount of activity going to the Defense Waste Processing Facility. To continue to be able to provide feed and to provide relief to problems with tank volume in the tank farms, Savannah River has come up with a number of innovative interim solutions to continue to process waste while the salt waste processing facility is being completed. And let's see, those go by these two acronyms. DDA is deliquification, dissolution, and adjustment. In that process, the supernate is removed from a tank. The interstitial liquid in the salt cake is also allowed to drain away and is pulled off. And then the salt cake itself, which you saw on a previous slide, actually has very low amounts of activity, is dissolved, has its pH adjusted, and then is low enough in activity that it can be sent directly to saltstone to be made into grout. The second interim process that was started up
and was mentioned earlier today is
is called the actinide removal process and the modular caustic side solvent extraction unit. That's a mouthful. That is a two-step process. So the DDA, the deliquification, dissolution, and adjustment, is a process that we could use to process some very low activity material. ARP and MCU allows us to move to slightly higher activity, higher amounts of radioactivity, and to also process some actinides. That's the ARP. The actinides are removed by adding monosodium titanate to the tanks, which absorbs the actinides, and then filtering that material as part of the process. The remainder of the liquid material then goes through the caustic side solvent extraction system, and the high cesium content material is returned to the tank farms to go to the defense waste processing facility, and the low activity material again goes to saltstone. So those interim salt disposition processes have been used by Savannah River to continue processing high-level waste, while the salt waste processing facility, which is scheduled, I believe, to go online next year, is, I did say scheduled, right?
24 tanks of current land base.
20, okay. Well, see, I've been, that shows you I've been out of the loop for 9 months, so. So because of that extended time period, the site is also looking at whether or not they can use these methods for a longer time period. Okay, so the 51 storage tanks, as I said, 2 of the tanks have been closed. 5 are in the process of being closed when I developed this material last year. 44 are in active service. They're underground, they're heavily shielded, and 43 of those 51 do have secondary containment of 1 degree or another. I think we went through most of this material on the disposition of each of the materials. That's just a long shot of the Defense Waste Processing Facility, the canisters that are produced by the Defense Waste Processing Facility, and this is an isometric view of the MCU portion of the ARP MCU facility.
How many canisters they produced today?
Well, I know in late October of last year, they reached 3,000. I don't know how many. They probably added a couple hundred. Yeah. So approximately 3,000, and those 3,000 contained about 31 million curies. That was the figure as of October of last year. This is what the melter in the Defense Waste Processing Facility looks like in schematic. This shows a pour that was actually, this picture was actually taken from the prior, the non-radioactive prototype for the Defense Waste Processing Facility, and that shows you what the melter portion of the Defense Waste Processing Facility looks like. Shows you the machine used to move canisters within the glass waste storage facility at Savannah River. This is where these canisters are stored in a vertical configuration until there is a geological repository to take them.
I might mention that canisters on the right are empty.
Yeah, that's why that guy can be so close to them. Absolutely. Present challenges that the Savannah River is facing. without changes to processing rates, all the sludge could be vitrified before salt processing is complete. That's a difficulty because recycle streams from the salt waste processing facility are intended to go to the defense waste processing facility, so that will require continued work on the site flow sheet. As we've already discussed, salt processing, the salt waste processing facility is behind schedule, and they are looking at ways to handle interim treatment methods. There is an issue with plutonium limits in the glass. In the analyses that were included with the license application for Yucca Mountain, the assumed plutonium content for the glass was a very interesting and round number, 897 grams per cubic meter. Before the license application went in, there was a movement to move that number to 2,500 grams per cubic meter, which was a lot closer to something that's supportable from a criticality safety analysis standpoint. That work did not get done before the license application went in, so there is still decision-making ongoing as to when and how the department will make the decision to move to a higher plutonium limit. At least that was what I saw in the literature up until recently. Is that still true, Pat?
Which one did you ask me?
Okay. The Canyon definitely wants it to go higher, so.
Yeah, the PU limit in the glass is not a problem for dispositioning the existing waste in the tanks in the Savannah River. It only becomes an issue if the department decides to dissolve plutonium as part of the excess plutonium disposition mission and send it through the waste system at Savannah River. So depending on the outcome of those decisions, it may or may not be an issue.
Okay. And then, of course, tank closure is a challenge at Savannah River, just as it is at other places in the site, to get both regulator and stakeholder alignment behind the maximum amount of material that can be removed. The Hanford site, quick site history. Constructed in 1943 as part of the Manhattan Project, 9 reactors were built on the site to produce plutonium. That irradiated fuel from those facilities was sent to 6 separations facilities, a number of which you were introduced to in your chemical processing lectures this morning. Special nuclear material was recovered for weapons purposes. I already discussed the fact that waste was neutralized and sent to the tanks. There's still a significant fission product inventory in the tanks, and a third of that, as we discussed earlier, is actually represented by the cesium and strontium capsules that are stored in the waste encapsulation and storage facility that is at the back of B plant at Hanford. Those numbers you've already seen on the pie chart. 177 tanks, all underground, all carbon steel. At Hanford, 149 of the 177 are single shell tanks. 28 are double shell tanks built during the time period of the late 60s through the mid 80s. And as at Savannah River, they have sludge, salt cake, and supernate, and we have the capsules. That's what the Hanford tanks looked like before they were covered up with their overburden. High-level waste disposition issues. We talked about where the capsules came from. They are about 3 inches in diameter. They're about 21 inches long. The capsules are double contained in stainless steel. 130 million curies total in the approximately 2,000 capsules, cesium chloride and strontium fluoride. The plans for this material have gone back and forth between needing to be further processed and whether the material would be satisfactory to go to a geological repository as is. This is yet another situation where without a geological repository and a specification for that material, DOE is having to reevaluate whether or not they want to continue to maintain and store what is fairly highly hazardous material for another 20 to 25 years in a facility that was built in the early 70s and is attached to a facility that was built in the late 1940s. There is the possibility of some of the 177 tanks being able to be processed as transuranic waste. That is something that requires significant regulatory work before it could occur. What that tends to mean is that this material gets pushed later in the processing schedule for the waste treatment plant, which we'll discuss in a moment, so that this type of work can potentially be completed and that material go through another disposition path. This is a very high-level flow sheet of the planned flow for high-level waste at Hanford. It shows over here the potential for material to go to the waste isolation pilot plant as transuranic waste. It would be either contact handled or remote handled transuranic waste depending upon what its radioactivity levels were. Similar in overall scope for Savannah River, there is a pre-treatment facility at Hanford, where the pre-treatment at Savannah River right now in interim salt processing is being done in tank or near the tanks with the small ARP MCU system. The plan at Hanford for at least the last decade and a half has been to build a large nuclear chemical processing plant to be able to split the material into a high activity stream to go to high level waste vitrification and a low activity waste stream which would also go through vitrification at Hanford. We could get into a long discussion on why that is, but we're not going to because I can't explain it. So, just to quickly go through some very similar material, the salt waste at Hanford will go through filtration to remove suspended solids. It'll go through ion exchange to reduce the cesium-137 concentrate. The solids and the cesium-137 will go to high-level waste vitrification. The decontaminated salt solution to low-activity waste vitrification. The sludge is going to be pre-treated in the pre-treatment plant to reduce sodium, chromium, and aluminum, which are materials that cause difficulties in making glass for a number of different reasons that John Vienna will explain to you in detail tomorrow morning. The sludge solids will go to high-level waste vitrification, just like DWPF. The low-activity waste is planned to be vitrified. So the challenges at Hanford are because the Hanford plan is to vitrify its low-activity waste. The present flow sheets show high amounts of sodium hydroxide required to leach aluminum out and to keep it in solution throughout the chemical processing system. This is the major things that is driving high numbers of low-activity waste canisters at present. It's also a major area of research and technology development and EM to try to deal with that issue, both getting more material into glass and developing means to remove the sodium. Also developing means that require less sodium to keep the tanks at a high pH for corrosion control reasons. Double shell tank space can be limiting as the site moves to retrieve more and more waste from single shell tanks. That's an interim process at Hanford to reduce the likelihood of leaks from those tanks that don't have double containment. And the waste treatment plant is now scheduled to go online in 2019. There are certainly a number of challenges that the site will be conquering in between now and then to put online what are 5 major nuclear facilities in the space of 2014, 2015 to 2019. So basically 1 facility per year to go through testing, operational readiness review, and getting ready to be put in commission. It's a very challenging schedule that they're looking to try to do some improvement on. And a path forward for the cesium and strontium capsules is needed. So the next category, we're going to talk quickly about transoceanic wastes. Transoceanic waste, we already said, not high-level waste, more than 100 nanocuries per gram of alpha-emitting isotopes of greater than 20-year half-life. Transuranic wastes in general come from 3 major types of facilities. They come from used or spent nuclear fuel processing plants that separate plutonium from uranium, Purex type plants, and from mixed oxide fabrication facilities. Both of those, as we've already discussed, are not done in the United States right now, but we are building a mixed oxide fuel fabrication facility at Savannah River. So in the future, there will be a transuranic waste stream that will come from that mixed oxide fuel fabrication plant in Savannah River. But where the lion's share of the transuranic wastes came from in the United States was from plutonium processing for weapons purposes.
Steve?
Yes.
Mixed oxide fuel fabrication facility, is that going to be government waste or is that commercial waste?
The mixed oxide fuel fabrication facility is the plutonium that goes into the mixed oxide fuel is all going to be ex-weapons plutonium. This waste runs the gamut from booties to protective clothing, used equipment that was used to process plutonium, equipment was used to fabricate plutonium parts, cleaning materials from the D&D of Rocky Flats. Because of the solvents used for much of this work, a lot of this material has the potential for having RCRA constituents as well. I'm not going to go through all these bullets, but the waste acceptance criteria for WIP have been set up so that we know what is in the material that is in place at the waste isolation pilot plant to a very high degree of precision. There are only certain types of containers that can be placed at WIP. The radiologic properties of the waste have to be comprehensively characterized, both as to type and amount, and that allows the WIP to determine what material goes into the contact handled category and what is remote handled transuranic waste. The physical properties of the material to be able to evaluate and make sure that it's going to be stable for long-term storage. Similarly, the chemical properties to ensure that there are not hazards or potential hazards. gas generation and record keeping for the long term. This is, in general, what the repository looks like on the left. The stacking configuration for one category of containers on the left for contact handled material. For remote handled material, they actually bore holes in and place the material into the holes, and that shows you that the transportation configuration for transuranic waste, the waste has been transported from all over the country to Carlsbad, New Mexico, where the waste isolation pilot plant is located. High-level waste disposal. We're gonna have an entire discussion of the geological repository issue tomorrow. So this is just to talk about disposal as a part of the overall waste system. There are only 3 classes of disposal destinations discussed in the regulation. That is, amounts that are so low that they can be released to the environment, for example, through the sewer system. Levels that are sufficiently protected by near-surface burial, and levels of radioactivity and activity that require deep geological disposal. The requirements from those are discussed in the Code of Federal Regulation and DOE equivalent DOE guidance. Near-surface disposal is the destination for things such as mill tailings and low-level waste, where deep geological disposal is required for transuranic waste, high-level waste, and spent or used nuclear fuel. Greater than Class C low-level waste is presently the subject of an environmental impact statement by the Department of Energy to determine what the appropriate means of disposal for that class of low-level waste is. In general, the situation on disposal of high-level waste and used nuclear fuel or spent nuclear fuel is that, as Alan Croft said earlier, the U.S. is currently producing about 2,000 metric tons of heavy metal per year of spent nuclear fuel. We also have a large volume of defense waste that is estimated to be converted somewhere between 15 to 20,000 high-level waste canisters. These are wastes that are destined for deep geological repository. The Deep Geological Repository Program actually significantly predates 1982, and the lecture tomorrow will go back further into history. This just notes that in 1982, Congress passed the Nuclear Waste Policy Act, directing the department to evaluate repository sites and select one to be developed. That process was short-circuited, terminated. There are many other terms that are used to describe what happened in 1987, but let's just say the law changed in 1987, and Congress directed DOE to characterize only the site at Yucca Mountain, and if deemed to be suitable, then to submit a license application to the NRC for that site. Also, in 1987, the Waste Isolation Pilot Plant Land Withdrawal Act was revised to stipulate that that facility should not be used for used or spent nuclear fuel. DOE submitted the license application for Yucca Mountain in 2008. In the fall of 2009, the department announced that it was going to withdraw the license application. That action is in court under 2 separate suits. The Nuclear Regulatory Commission has not formally accepted the DOE withdrawal, and there are people in this room who know a lot more about that than your lecturer. There are major players in the ongoing saga of that. They include the Atomic Safety Licensing Board at the Nuclear Regulatory Commission, the Commission itself, the Secretary of Energy's Blue Ribbon Commission on the nation's nuclear future. So the admonition there is to stay tuned. That's an overview of the Yucca Mountain site just north of here. This just is intended to show you the scale of the equipment that was used to bore the test holes at Yucca Mountain. And an overview at the bottom, just to show that, I mean, it was certainly a very complex problem that was being worked. There was there are a number of different waste packages that needed to be arranged so that that thermal loading limits of the site were not exceeded. So that's just one emplacement concept for the facility. As I said, we'll discuss that more tomorrow. Very quickly through low-level waste to get you guys out here on time. Low-level waste is basically not any of the above that we've discussed. It tends to be, that's a common drum of low-level waste. It can be anything from normal operating materials such as anti-seize to old equipment that needs to be accessed, quite a broad variety of waste forms. It comes from DOE, ongoing facility operations, protective clothing, cleaning materials, etc. The largest volumes of it come from the Department of Energy's D&D and environmental restoration programs. That produces huge spikes in the amount of low-level waste that have to be buried. And certainly, over the last couple of years, the large amount of D&D work that was gone under the Recovery Act really spiked the amount of low-level waste that was buried. Commercial nuclear plants have similar operating wastes to those of the DOE's operating nuclear facilities. There's also waste that comes from medical facilities, from diagnostic materials, and waste from the administration of nuclear medicine. There are industrial uses, gauges, radiography. All these add to the amount, but from a volume standpoint, the Department of Energy predominates in low-level waste. These are some numbers that give you some quick distributions. The 1998 split of waste showed DOE at about 2/3 of the waste produced. That varies from year to year. I think in the last 2 years, the Department of Energy probably would have been up closer to 75 to 80% of the low-level waste produced. And it goes to, at the moment, 3 low-level waste sites licensed in the United States, and we'll show you where those are on a subsequent slide. Low-level waste is divided into several categories under NRC regulation. Class A is the least hazardous and has the least stringent requirements for disposal. Class B moves on to more hazardous, short-lived waste, and these are guidance to be used for the performance assessment of disposal sites. We have an entire lecture tomorrow afternoon on performance assessments of disposal sites. And this just tells you some of the materials that fit into the categories: filter sludges, evaporator concentrates from processing material on nuclear power sites. Higher activity resins meet Class C requirements, and sealed radioactive sources often meet the activity requirements for Class C low-level waste. This shows you what trenches, what the material looks like as it's emplaced. You can see this is sturdy containers, can mean banded wood containers. Those are metal containers at Barnwell. And this shows probably Class B waste at EnviroCare, because you can see they're actually adding grout to it to stabilize it, so that's what indicates it's not Class A waste. You wouldn't do that if it was Class A. These are the general disposal requirements that are discussed by the NRC in 10 CFR 61. I won't read through them. They read an awful lot like the waste isolation pilot plant requirements, because they're intended to keep the material stable over the time that it presents a potential hazard to humans and the environment. The presently operating disposal sites are at Barnwell in South Carolina, at Clive, Utah, indicated number 2, and at the Hanford site in Washington, indicated by number 3. I do note that there is a newly licensed facility in Texas that is getting ready to go operational this year. Low-level waste can become a political football, and I just note that in 1979 this became particularly acute. The 2 western sites in Utah and in Washington State were closed down temporarily because of shipping docket problems with waste unsatisfactorily characterized. With the amount of material that started to flow into the Barnwell facility at South Carolina, the state of South Carolina decided that they had no desire to be the nuclear waste dump for the entire United States. So they imposed volume restrictions, which it was worried was going to lead to shutdown of that facility. When you add in the general public worries about nuclear waste, you get the nuclear waste, the Low-Level Radioactive Waste Policy Act of 1980 as further changed in 1985. And the intent of that Low-Level Waste Policy Act was to make low-level waste disposal the responsibilities of the states working together to develop what were called compacts to handle the wastes in the areas that it was being produced. There are a number of very good books on the subject. I will summarize it to say that in between 1980 and last year, there were no new low-level waste disposal sites licensed, and you will see, and you see from the previous map, that they still are not really geographically dispersed. They are in fact not in the areas that have the most numbers of nuclear power plants in them. But with all the dire predictions that were made in the late 70s and 80s, why are we not awash in low-level waste? Well, we're not awash in low-level waste because there's been substantial improvements in the technology of treatment of low-level waste to produce waste streams that can be direct discharged to the environment, and much less waste that needs the protection of shallow waste disposal. There have been administrative requirements where through management methods, much less waste enters the system, so to be categorized for potentially becoming low-level waste. The type of technology used to treat low-level waste, it depends on its nature. Basically, normally broken down into liquid, wet solids, and dry solids, with the processing methods shown in the parentheses. And economic factors, doing waste minimization versus treatment is often a trade-off of capital expenses versus operating expenses.
That's probably your biggest driver though, right?
Pardon?
That's the biggest driver.
Which one?
Economics.
Yeah, I mean, this is the cost of disposing a low-level waste has doubled and redoubled since the late 70s, so it has been an enormous driver to produce less waste and to segregate waste more efficiently and more effectively. Another thing that when early in the nuclear power business, it was thought that incineration would be a major volume reduction method to avoid large volumes of low-level radioactive waste. Incineration of nuclear waste is still done to some degree in Europe. It is not done in the United States as of 8 months ago. The last incinerator licensed to incinerate radioactive waste in the United States was the Tosca incinerator at the Oak Ridge Reservation in the U.S., which took care of mixed low-level waste for about 15 years. Incineration of radioactive waste was a victim of overall incineration problems with hazardous waste in the United States. It's now incineration in general is now a niche player in the United States. It's only used for waste that can't be treated in any other way. The most frequent one is hazardous medical waste is still incinerated. But the concern is you're giving up a method that had great volume reduction capacity. I mean, 20 to 1 volume reduction capacity you could get through incineration. There have been a couple of competing technologies. I'd list fluid-based steam ceramic forming as one of them. There is wet air oxidation, which is a high temperature, high pressure process that produces volume reduction and is used for some low-level waste spent resins in the commercial nuclear community. And I put vitrification up there because not in the United States, where we have an awful lot of land that can be used for shallow waste burial, but in places like South Korea, where they don't have the benefit of having large amounts of waste that they can use for shallow waste burial, the South Koreans are vitrifying low-level waste and to both put it in a form that is suitable for what is a very saturated geology in South Korea, and they get a substantial volume reduction very similar to incineration when they vitrify solid low-level waste. Greater than Class C, highly activated components from nuclear reactors can be have enough radioactivity to be greater than Class C, and some very high activity sealed radioactive wastes. They also can come from decontamination of facilities other than plutonium facilities. The greater than Class C environmental impact statement was issued by the department last fall, and it evaluates the listed sites as a potential sites for greater than Class C materials to be sent. In addition to deep geological repositories, there are a number of other potential disposal technologies that are included in the draft environmental impact statement. Just one quick slide on a special category of waste, and it was created by a new law in 2004, although the Department of Energy would state that they had the ability to do this in accordance with the Department of Energy's Order 435.1, all along. In 2004, Congress actually put into law that certain materials associated with high-level waste that had been reduced in activity sufficiently enough not to no longer require the protection afforded by deep geological repositories could be designated by the Secretary of Energy as waste incidental to reprocessing, or WIR. The process has been used at Savannah River to designate some classes of material not requiring deep geological disposal. The NRC is given a role in this process to work, as the law says, in concert with respective state regulators to oversee the waste incidental to reprocessing. That's a mouthful process. It does not apply for Hanford because negotiations in making the law could not, the Washington congressional contingent did not agree with the change to the law, and what it requires is the determination of a satisfactory processing method and waste disposal method. It uses performance assessment to show that the combination of processing and disposal method provides adequate protection. And Jim Clark will discuss the performance assessment process tomorrow. Concluding low-level waste thoughts, although you can think that time has stood still since 1985 because on the low-level waste front, because we don't have any more disposal sites yet, I hope that the last 15 minutes has showed that there has been some progress in that field. There's been continued refinement of waste classifications. Incineration may be out, but there are high-end volume reduction processes that are available to handle certain classes of low-level waste. And that from a performance, when we look at the overall waste processing system, what is okay is a combination of specific activity of the waste, the form, the final form that the waste is put in, and the characterizations of your disposal method. Those are the three factors that are looked at to determine whether or not a situation provides adequate protection. Okay. A quick run through the regulation. The players in the regulation game in our business include the Environmental Protection Agency, which develops generally applicable standards for radioactivity at the boundaries of facilities, and also provides a direct regulatory role at the waste isolation pilot plant. The Nuclear Regulatory Commission, which is the regulator for civilian nuclear facilities and provides, and some Department of Energy facilities. The mixed oxide fuel facility will be regulated by the Nuclear Regulatory Commission, and also has some advisory roles at DOE activities like as described in the waste incidental to reprocessing process. The Department of Energy also regulates nuclear safety under its rules, and since the rest of the discussion is focused on commercial nuclear regulation, I'll just go quickly through. The department regulates nuclear safety under 10 CFR 830, Part A, which covers quality assurance and unreviewed safety questions. Part B, which addresses documented safety analyses, what are safety analysis reports in NRC space. It regulates radiological protection under 10 CFR 835. Radioactive waste management is covered by DOE's Order 435.1. And The regulatory regime for nuclear safety and radiation protection is administered by the Secretary of Energy by the Office of Health, Safety, and Security, which provides independent oversight, enforcement, development of DOE rules and standards, and oversees the department's integrated safety management program. This is a schematic diagram that NRC uses to describe how it regulates, how the regulation is established initially by regulation and guidance and enforced and emplaced by licensing and certification processes. Oversight is provided by not only NRC personnel on site, but NRC personnel at regional offices throughout the United States. And that operational experience is used to provide risk-informed insights to the regulatory process. I would say that the Department of Energy would say it uses a similar process for its regulatory regime. Reactor licensing is done by the NRC under 10 CFR 50. The process which most nuclear reactors in the United States were licensed under is a two-step process which required both a construction permit and an operating license, as described in the license in this view graph. The new regulatory regime is intended to move the one-step process into the two-step process into a one-step process and reduce regulatory uncertainty on the part of the entities being regulated. It allows for a combined operating, a construction and operating license. Which can be augmented by an early site permit that allows certain amounts of civil site preparation and civil construction to go on. And one of the features of it is a design certification, which certifies a specific reactor design for use to be constructed. So if you've been following this at all over the last 5 to 8 years, a number of reactor designs have gone through the design certification process with the Nuclear Regulatory Commission to be, the vision is an off-the-shelf product that a licensee can take to the NRC and say, that's the plant we're going to build. It's already been certified. Just a quick update. I think this was current as of last year. There have been 4 early site permits issued, 2 are under review, and 2 additional permits were expected at that time. The combined operating licenses of that number of applications and the reactor design certifications were completed for those 3 designs, and 3 reactor design certifications were underway at that time. I am not going to go through all of the, and you will be happy that I'm not going to go through all the regulations that pertain to nuclear fuel site facility licensing. I have listed them. They cover everything from mill tailings to high-level waste and spent nuclear fuel disposal. They address transportation, environmental protection, operators licensing, and on through to decommissioning. And I think I'll just conclude with this this slide that when you talk to regulators at EPA, at NRC, and at the Department of Energy, they describe 2 basic approaches to regulation. Best available technology is a technology-based approach, and that's where it says if you use this technology, it is approved for use. The example we already discussed briefly in this presentation is the best demonstrated and available technology that EPA has put in place for high-level waste, which is borosilicate glass. The statement is, if you make borosilicate glass to the quality specifications that are in the rule, then that is a satisfactory waste form for high-level waste. Much more frequently, the regulatory approach is performance-based. It's intended to show by analysis that a facility or an activity is safe, either through safety analysis, under 10 CFR 50 for the NRC, under 10 CFR 830 for the Department of Energy, or performance assessment for disposal options under both the NRC and the Department of Energy. I will leave you with probably the best source on regulation, and Alan Croft's not here for me to embarrass him because he's one of the co-authors. New Rig 1853 is probably the best history and overview of the regulatory scheme in the United States, absent reactor licensing regulations that I have seen written. I certainly, for understanding the regulatory fabric for radioactive waste in the United States, it is the single source, and it's an exceptionally well-written document. Thank you. And